Bismillahirrahmanirrahim. Welcome to this session. So this is the last class before your midterm of the advanced digital signal processing, and we'll restrict our syllabus up to this. In the last class, we have discussed on the syllabus issues. So I believe you already get the message from my side. Okay, if you have any other job to do, for example, midterm exam or other task, you may leave, and afterwards I'm recording this lecture. I will upload it in your Google Classroom. That is fine. Okay. So today we'll just discuss about the derivation of all-pass filter and also the application. In the last class, we have discussed about the linear phase, non-linear phase concept. Also try to clear it up, how the group delay been actually represented in our practical life. What is the physical meaning of the linear phase, non-linear phase, and from that point of view, how the signal may face the challenges when you want to retrieve the signal back. Okay, so those are the things we have already discussed in the last class. I believe that you understood that. If you have any question from the last class or any part of the syllabus, you are always welcome to raise the question. Before raising the question, just raise your hand so that I can give you the floor. Okay. Okay, let's start today's topic. This is IIR all-pass filter. As we have already known that whenever we are processing something with a IIR conventional filter, always we have got the output as a non-linear phase response. And to cover this up, what we have planned, we will plan to put IIR filter and then a all-pass filter to make it combinedly as a FIR filter. In a sense, this all-pass filter is also a nonlinear phase response, given a nonlinear phase response. That's why this is also one kind of IIR type filter. One characteristic of all-pass filter is that it will pass everything. So that means in the frequency domain, if we talk about the frequency domain from -pi to +pi, that is our range of view, it will pass everything. So the magnitude of the all-pass filter is 1. What about the phase response? This is the magnitude response. You can write in this way, H omega, the magnitude. And what about the phase of that? That is the important part, from -pi to +pi, or you can say 0 to pi, whatever the case. In that case, it can be anything. Okay, you can design your all-pass filter in such a way so that we can make it a linear combination whenever it cascade with an IIR filter you have already designed. Yes, 0 to you may leave, no problem. And those who have the exam. Okay. Now let that the transfer function for a all-pass filter is AZ. We can take it in the Z plane, anything. And the normalized function is this. You can, first of all, neglect this term, normalize. Just think that we have a filter. We have a filter, HZ, that is the all-pass filter. And now we are taking a function, Z to the power -1. We know that. What is that? And that produce the output is equals to 1, which means that this is known as the inverse function of HZ. Inverse function of HZ. How to find the inverse function? In any cases, you are designing a filter which is like conventionally HZ1, and you can put an inverse filter HZ2. How it works? Let's say you have your input Xn, you got the output Yn. What the inverse filter do? It will produce the Xn back. That is the definition of the inverse filter. Now, whenever you are multiplying these two, if you multiply these two, what will happen? These actually give you the amplification or the gain. The gain is definitely 1. So HZ1 into HZ2, Z2, that should be give you the magnitude 1 for any frequency. And based on that situation, we are taking if this is the all pass filter. Let me make it a little bit large. Okay, if this is an all pass filter, this is the inverse function, and this is equals to, of course, this is equals to 1. The later part of the lecture, we can also draw this. Okay, no problem, and we can prove it. Okay, how that actually been worked. Okay, based on this equation number 1, we can say that, of course, this if this magnitude of this multiplication is 1, then we can say that this the power of this filter is equals to 1 for all the frequency value. And now the vital question is, the vital question is, what about the phase? That is the question. Because the amplitude is 1 everywhere. Amplitude means that actually passes everything. What about the phase? It can be anything. You can design the phase with any value. Okay, 07, if you have the quiz, midterm, you can also leave, and later on you can download the video lecture, and that is enough, no problem. Okay. Here, what we can write, of course, any function can be represented with the poles and the zeros in the Z-plane. Of course, that is true for any sort of filter. So this is nothing special. And this is for n order. So that's why we are putting this number n. Similarly, we can write it very easily by replacing the value of Z is equals to Z to the power minus 1. Okay, now when we will multiply these two, we already know that that is equals to 1, and now we have we have this pole zero combination for these two function, so that will of course produce this output. We need to know that for the all pass filter, these are the zero locations and it shows the pole locations. And for the inverse function, these are the zero locations and these are the pole locations. How they are related to each other in convention, what we can write, let's say if I put 1 plus Z to the power minus 1 is my filter. What does it mean? We already know that this is 1 divided by Z. So Z plus 1. So it fills that, it shows that where is the zero location at Z is equals to minus 1, and where is the pole location, that is at the center. So now if I put H Z to the power minus 1, so Z is replaced by the Z to the power minus 1, then it will give 1 plus Z is now replaced by Z to the power minus 1 to the power minus 1. So that is the case. So in that way, we can understand how they will change their position. So now definitely from this equation, you can also find what are the pole location and the zero location, isn't it? So it is very easy to understand. Okay. Now from this equation, let's say this is star. So from that equation, we can derive this relation between the zero locations and the pole locations. Okay, if we can do that, of course, by doing this, we can understand what is the value of PNZ and what is the value of QNZ. If you can think about this, if you can find PNZ and QNZ, in future we can find some relation between these two. Then of course you can find PNZ to the power -1 and QNZ to the power -1. This is very obvious. So in which condition this will valid? Okay, so this star marks how we can make it valid for a particular case when we have some target to meet that target, how we can make this condition satisfied. So that is our main job. Our task is to design a all-pass filter which has the magnitude is 1 for all the value from -pi to +pi. That is true. And also we need to have a control over the phase value. So that is the message. So we have two things. One is we need to make a control over the phase, and other thing is definitely that should be valid for this equation. Otherwise, that will not be valid for this equation. Okay. So this equation is very important because it shows that we got the magnitude is equals to 1 for all the frequency component. Okay, let's take a first order all pass filter as an example. So we took it, the AZ is equals to K 1 plus AZ to the power -1 and 1 plus BZ to the power -1. Okay, we can take it here A and B. That shows that, okay, of course there is a pole locations and we are setting the 0 locations. You know that A is related to the 0 location and B is related to the pole location. This is obvious, and that's why the B should be less than 1 for make it a stable system. So we know that if this is our unit circle, all the poles should be inside the unit circle for the inside the unit circle. Okay, the ROC would be like this. If this is the unit circle, the ROC should be like that, where the unit circle should also be a solution. So if I show it in a bigger version, you already know that this is the unit circle. This is the unit circle. And where the pole should be, pole must be inside the unit circle, so that the ROC for which kind of signal? For the causal signal, the ROC should cover the ROC will cover the unit circle. That shows that the system is stable. So based on that, of course, the value of B should be less than 1. That is the only condition. So now, what is the task based on the previous conditions and this new condition? We will design our AZ. That is the target. We are putting a variable K there, which will be a constant for a particular filter. Okay. Now from the Z domain to the frequency domain, we are putting the value of Z here, and Z is equals to e to the power minus j omega. So we put that value, and according to the Euler's identity, Euler's formula, we can elaborate that function. And now we also know that the power spectrum of the all-pass filter can be written like this, and we know that this should be is equals to 1. That is a condition we already know. So from this equation, we can write this equation. Okay, fine. Now we have this equation from the power spectrum point of view. A e to the power j omega, and the magnitude square is equals to this. So this is our fundamental equation we have derived. from this equation, what we can understand, what should be the output? The output should be is equals to 1. Certainly, it should be is equals to 1. So if we take k is equals to 1, here k is equals to 1, and a is equals to b, of course, you can see k is equals to 1 and a is equals to b. It is, of course, then they will, all the values will cancel each other. And of course, we got 1. However, that makes some kind of problem. What is the condition? I'm writing the condition here. A is equals to B and K is equals to 1. That is those are the conditions. If that is so, then if we look back to our filter, this is a first order filter, what we have found, K is equals to 1, this is equals to 1, and A is equals to B. Let's say this is equals to A. Then what will happen? This AZ is equals to 1. AZ equals to 1 means, yes, you can write in this way, AZ is equals to 1 plus J0. That means you don't have any imaginary part. So that is not a complex signal. This is a real part is 1, and this is an integer. It shows that you only have the magnitude. This magnitude is equals to 1. That is true. Okay, this is an all pass filter, but that is a short circuit. So you have this point and this point, and you are making a short circuit. This is 5 volt and this is 5 volt. That's it. What about the phase? You don't have any imaginary part that shows that you don't have any control over the phase. And that is the problem. Okay. So in this equation, if we let k is equals to 1 and a equals to b, that will not help us to design the all pass filter. Yes, it will satisfy that the magnitude is 1. However, what about the phase? The phase will not be controlled by this condition. Okay, now there is another way to satisfy this is equals to 1. How? One is a can be taken as 1 by b and k can be taken as b. Okay, so it will be b square, and whatever, you can change a as 1 by b, this will be 1 by b. So of course, in total, this will be b, so b over b. And of course, you can change this value, a is equals to 1 by b and this is b. In that way, you can find that they will also cancel each other. So in that way, we can prove that this is equals to 1. There is no problem. Now writing these two conditions, k is equals to b and a is equals to 1 by b, what happened to our actual equation? Yeah, this is the equation. What happened? Now put k is equals to b, so it is equals to b, and a is equals to 1 by b. We have 1 by b, so I can write in this way. So now az is equals to k is equals to b, and 1 plus a is equals to, you can put a or b, any of those. Okay, I can put a there, a z to the power minus 1 divided by 1 plus b is equals to 1 by a. Let's say 1 by a z to the power minus 1. Or in another way, since this we have b there, so all the values should be converted as b. A is equals to 1 by b, so I can put it like that, and this is equals to b. So finally, we can get b divided by 1 plus 1 by b z to the power minus 1 divided 1 plus b z to the power minus 1. That is the function we have found. And now what we observed here, we have both the magnitude part and also we have the phase part, because z is equals to e to the power j omega, so we have that part as well. So we have the phase part in this equation. Try to understand that this equation only gives us the feelings that we have the magnitude 1, and what is the actual filter. This is the actual filter. We let that this is our all-pass filter, and putting that condition, k is equals to b and a is equals to 1 by b, we have found that we have both magnitude control, which is 1, and also the phase control. So at last we got this equation, simple equation. So this is our filter. This is what kind of filter? This is our all-pass filter for any value of b which is less than 1. You can choose any value. You can choose any value. Let's take an example. Let's take an example where are the poles and the 0, b plus z to the power minus 1 divided by 1 plus b z to the power minus 1. We can write it like this: bz plus 1 divided by z plus b. That's it. So from there we can find z is equals to minus 1 by b, and z is equals to minus b. So this is equation number 1. From there we can find the 0 location. This is equation number 2. From there we can find the pole location. And if you want to draw that, if you want to draw the pole and 0 location, these are the unit circle. So let's find first put the pole location. This is the pole location. Of course, that is less than 1. So let's say this is a minus b, and we have 1 minus b. Here is, let's say this is our 0, which is minus 1 by b. If you took any value, for example, if we are considering any value, let's say it is a minus 0.5, then of course the 0 location should be at 2, minus 2. So if you are shifting this 0 very close to the pole very close to the center, of course this 0 will go apart. If it is extended to very close to the unit circle, it will be also very close to the unit circle. For all the cases, the magnitude response should be remain constant. However, we can control the phase by changing the value of the pole and the 0 location. That is the beauty of the all-pass filter. So we have both magnitude control and also the phase control by this kind of filter. And now you can also see that there is a very good relation between the poles and the zeros. Okay, so they have a very good relation. So it's very easy. If I put a pole there, suddenly without knowing anything, I also know that there is a 0. If I put a pole here, I suddenly know that there should be some 0. So they are couple, they makes a couple, and they makes a couple, like that. Always. In the left side, again, if I put a pole here, of course I have a 0 there in the ring, and they makes a couple. Okay, so they have the relation like this, poles and the zeros having some relation. So it can be presented like this. Okay, we already know that it can be present in general like this, and where we can show that how these poles and zeros can be related with each other. So if we have, this is our qz, that means representing the pole location 1 plus b z to the power minus 1. What we are doing, z to the power q z to the power minus 1, that is of course 1 plus bz, and now multiplied with z to the power minus 1, that means it will be minus 1, and so that will give the value z to the power minus 1 plus b. And you can find that this is exactly, I'm taking another color, this is exactly equals to this one. So we can write it, this is equals to your pz. So what is the relation? So pz is equals to z to the power minus 1 q z to the power minus 1. So it is very interesting that if I can only find qz, that means the pole location, we can directly find the zero locations for the all pass filter. That is another beauty of this kind of filter. So that is all about for the first order filter. We have done it. It can be shown that for nth order filter, we can extend the things like this. Okay, so this is the common equation, and you can extend it like this. Okay, probably there's some mistake on these polynomials. Just you can derive it yourself, and you can find it very simple. And as I already mentioned, that there is a couple between the poles and the zeros, and that's why this is called, this kind of function is called the romantic function, because you have one pole and there are consecutive zeros. If the pole is changing their position, of course the zero is also changing its position. Okay, so they have a very romantic relation between the poles and the zeros. Okay. Okay. We have considering in this case, we are considering, whenever we are giving the example, we are considering the real pole and the real zeros. Now, what about if we have the imaginary pole? Of course, we should have imaginary zeros, and where it should be. For that, we can say that the equation can be right like this. In general, we can think this is for the first order, z to the power minus 1 minus c1 star divided by 1 minus c1 z to the power minus 1, where c1, as I have already mentioned here, if this is the pole location, this is an example, you'll find it. If this is the pole location, r e to the power j theta, how we can represent that? R is the magnitude and theta is the phase, and since there is a positive, so that means in the positive direction. So in the Cartesian plane, we can find that, okay, this is the value of r, this is the magnitude of r, and that should be shifted theta a degree, and that's why this is exactly the point. This is exactly the point for r e to the power j theta. Now, what about this is the pole location. We can find the pole location. Now, what about the zero location? Zero location for what? For complex pole location. The zero location is 1 divided by c star. So that means we have 1 divided by what is the value? We have r e to the power, so this is a complex conjugate, so e to the power minus j theta. So that relies on 1 divided by r into e to the power j theta. So it shows that again, previously the magnitude was 1. You can take r is equal, r is equals to, let's say, 0.5. Now 1 divided by r should be equals to 2. So let's say this is the value of 2. And now what is the proceeding? The proceeding is theta in a positive direction. So it will proceed in the theta degree, and this is your 0. So to be very more specific, what we can show, this is your unit circle for any pole. Let's say here, what we can find, we need to extend a line from the center, and we can find if this is the value 0.5, then the another 0 is at the location of 2, and this is the 0 location. As you already understand, or you have the idea that the imaginary poles should come in a pair. So if we have the pole there, of course, we have another pole at this position. So that's why we can have another 0 like this. Okay. So if I have given something like that for a all pass filter, let's give an example. This is very important. Let's say I have given this pole, and I told you to find out the complete the design of the all pass filter. Okay, let's it has shown that there are 2 poles, and complete the design with all the poles and the zeros needed to design the all pass filter. Then what are the other poles and the zeros? Of course, you should write in this way. Of course, there should be poles like this, and for all the poles you should have zeros, so they are making a couple and making a couple, and for this one, the rest one, you have another. So this is the way you can. So I have shown 2 poles only, but you are forced to design this all pass filter with introducing another poles and the other zeros, related zeros. So this is for what? This is for the complex poles. Okay. And now the question is how you can believe me that, okay, this equation also for the all pass filter. We have already proved something for the real poles and the real zeros. Now this is the section. You can just go through this section. I will upload this section with the video lecture, so that you can probably I have already uploaded this. Okay, so if I'm not, then I will upload this one. So for this particular filter, we can justify that the magnitude response of this filter is equals to 1. So it shows that, okay, what we have learned, that is perfectly all right for designing the all pass filter. This is the vital question: what is the use of all pass filter? I believe you already understand what is the use of the all pass filter. Okay, we have already discussed about the group delay and the phase delay, and we have learned about the use of that. Okay, now we can give another example based on all pass filter. Let's take an signal xn, which is sine 0.2 pi n plus sine 0.4 pi n plus sine 0.6 pi n. Of course, by seeing these 3 signals, we can find that this is a low frequency, this is high frequency, and this is the highest frequency. And they made the total signal xn, the discrete signal. Let's say this xn is passing through this LTI system, which is a filter. Of course, all the LTI system are the filters, and it has given that the group delay is equals to 300. That means 300 samples. Group delay is 300, or you can say the 300 samples. That means that it actually this is a FIR filter. The group delay is constant, means that is a FIR filter, and for that we got the linear phase response for this one. The rate of change is 300. This rate of change is for all the frequency. The rate of change is not a function of the frequency. That means it is a constant value. So for the higher frequency and lower frequency, you have the constant 300 delay, sample delay. It's mentioned here. Let's 0.2 pi. What is the delay? 300. 0.44 pi. How many delays it experienced? Then 300. For 0.6, it also experienced 300 sample delay. Now, let's say this is your time domain signal. Okay, intentionally, it's actually been given like this. Let's say this is the 0.2 pi signal. This is 0.4 pi, and this is 0.6 pi. By seeing the time domain signal, you can also understand that this is a higher frequency, this is a medium frequency, and this is a low frequency. As we already understand that all the frequency will face same amount of delay. So what would be, it starts from the 0. So what will be the starting point at the end of the output? Of course, it will start at the position of 300, because 300 is the delay. So from the 300 to some extent, so it will continue like this. For the second one, it actually starts at the location of 100. Now it should start with, it will be delayed for 300 sample, so it should start with 400. So it start with 400 there. Okay, fine. What about the last one? This start at 200, so added 300 delay, so it will start from 500. And at the end, what we have found that xn and this one is exactly the same, just there is 300 delay, 300 sample delay. So after 300 sample, you can retrieve your original signal back 100%. What you are targeting, you can get back your original signal. Okay. On the other hand, if you have nonlinear phase response, we have mentioned that let's say very high, medium, and lower, something like this. So this is from the time domain perspective. This is 0.2 pi, this is 0.4 pi, and this is for 0.6 pi. So as you can see that the rate of change here, the rate of change is very high. So that shows that this is the rate of change for 0.2 pi. Here the rate of change is medium, and that is the rate of change for 0.4. And this is rate of change is very low, and this is the rate of change is for that one. So it shows that different frequency are experiencing a different rate of change and different, I should say, the group delay. So different frequency are facing different group delay, and how that will react on this particular example. So with the same example, as we have already mentioned, this is the example we have. In the frequency domain, of course, we'll find 3 stem, because we have 3 frequencies. And now we want to draw this in the output. So as we already understood that this is 0.2 pi, this is 0.4 pi, and this is 0.6 pi. Now, if you you can also help me to draw this. So 0.2 pi, it actually experiencing 300 sample delay, and this experiencing 200 sample delay, and 0.6 experiencing 100 sample delay. So now the question is where this 0.2 pi signal will start. Naturally start with the 0, and it will experience 300 sample delay. So that means it will start at 300 sample. So the black signal will looks like this in the output. Now what about the green one? It start at 100, experiencing delay more 200. So altogether this is 300. So 300 sample delay means it also start at the same location, and the signal may be like this. The red one, it start with the 200 sample, already 200, and now experiencing 100 sample delay. So it also experiencing total 300 sample delay with respect to this zero line. So the red one also start from there. It's a higher frequency. Now we can see that it makes a lot of problem, isn't it? It makes a lot of problem. You can't actually retrieve your actual signal should be looks like this. The actual output should be like this: higher frequency, then lower frequency, and then lower frequency. Should be like that. It should be shifted, as we have shown in earlier example. However, for the non-linearity of the phase, we have found this kind of issue. So how we can solve this? Of course, we need to put a all-pass filter in such a way so that we can segregate our sequences. We need to put the delays in such a way so that the group delay should be is equals to all the group delay should be equals, whatever the number that should be equal. Okay, and that is how we can solve this problem. Okay, so please neglect this later part. Okay, so there is, do not go to this part. There are some mistakes or misconcept you'll find there. So that's why you can restrict yourself up to this. Okay, so you can find this all pass filter. You need to implement the all pass filter for solving this problem. Okay, just a minute. So for the filter design, we have the tools. What was the name? I forgot the name. So it was, let me search it. Okay, I have given it to your classroom. Probably that would be the fastest way to see that. Just a minute. Okay, so we have already talked about this software. Let me prepare this one for our purpose. Okay, we will look into this pole zero. Also, the time domain values are very important sometimes, but we'll definitely try to understand the pole zero stand. Okay. Where is, sometimes it makes problem, this software. Small window. This one. Okay. Okay, so first of all, we can take the blank, and we already know the process, how to represent the all pass filter. We already have all pass pole. So we can take it directly in the complex plane. So as you can see that, okay, you see that here is the pole, and there is the 0. I can put it in the I can put in the real axis as well, and you can see that whenever we are changing the pole location, it will also change 0 location. Okay, now the important fact is the magnitude response. This shows the magnitude, and you'll find that this is 1 for all the frequency, of course. And what about the phase? The phase part is our main concern. So you can see you can control the phase with this. Okay, how we can control the phase? Only not only by this is effective. Okay, you can make the phase in different. Okay, what we can do for practical purpose, let me start with like this. Let's take an let's design a real 0. I'm putting a real 0 here, and the real pole at the center. If I put it at the center, of course, this is not perfectly at the center. If we put it at the center, okay, then what we have found, the phase, if we can look at the phase value. We can just for this one, okay, switch off the magnitude portion. Okay, only the phase characteristics. We can find that this phase is linear. Of course, that should be linear, and we have found this is linear. Now, for a better kind of filter, because as we know that by using the using the IIR filter, we can improve the quality of the filter, and we can improve the quality of the filter like this. Okay, however, what is the problem? The problem is the phase is now non-linear. In any cases, the phase is non-linear. Okay, for the practical purposes, we can put this in the negative portion. Okay, we have this non-linearity. We have the non-linearity that should be there, and you can find this is linear FIR filter, and this is a non-linearity. Okay, what about the group delay? You will find there is a group delay portion. Okay, this black one, this one is the group delay. You can change it, and you will find the group delay. As I put it in the center, you can find that the group delay is constant. You find the group delay is constant. Whenever you have the non-linearity, you'll find that the group delay is changing. What does it mean by this group delay? Here, for the low frequency, the delay is low. For the high frequency, the delay is high. And this is classically that's supposed to be. For the lower frequency, the delay is low, and for the higher frequency, the delay is higher. And now the question is, we need to design an all pass filter so that we can counterbalance this. Okay, so now what we can do, we can introduce an all pass filter there. Okay, so this is our new filter. So this portion for the actual IIR filter you have already designed, but we have found some problem in the group delay, or you can say in the phase. So now what we can do, we need to solve that. Okay, so how we can solve it? Try to understand it. Okay, to my understanding, to my understanding, it almost solved the problem. Okay, you found that almost all the places here, yes, there are some problem. Of course, you need to define the frequencies. Almost from the 0 to very higher frequency, there the group delay is remaining constant, because you can find that the phase response is almost linear from almost 0 to some other values. Okay, you can tune in a way so that you can find the linearity almost all the places. Okay, if you found that, okay, no, this is not enough for a particular all pass filter, then what you can do, you can introduce another all pass filter there. Okay, the things would be more complex, but in some places, okay, you can see there. Okay, so by some means you can see that, okay, there are some little changes, still they are very close to the constant value. Okay, the delay is almost here, the delay is almost the three samples, and by tuning and turning, you can put the constant value. As a researcher, you probably know that for which range of frequency you should care about more. So you can target that frequency practically, and you can solve that problem. Okay. So this is the full story. Here we have two filters. One is all pass filter, and another one is our conventional IIR filter, which help us to design to do our particular job. So first, IIR filter is to give us the strength to filter it out, and the second all pass filter give us the advantage of this group delay constant. Otherwise, there is some distortion, which is known as phase distortion. Okay, so for today, that is the last part we have already completed. So if you have any question or any comments on today's lecture, or in full range of the lecture, we can discuss about that. I have already discussed about the syllabus, so please give me a time. I have mentioned that in the next week we don't have any class, so we can take a gap there for the next week, and next to next week. So in between 12 to 18, you need to give me a time so that we can conduct the midterm. And just after the midterm, from the 23rd of September, we'll start our class again for the final term. Okay, I believe everything is fine. Okay, thank you.